We're going to be introduced to systems of linear equations. We're going to look at 2 and 3 variables in particular, and we're looking at the Cartesian equations. Now, if we write Cartesian equations in two-dimensional form, we might get something like these two equations here. So we have two equations in two unknowns, the unknowns being x and y. So they're linear equations, and they're written not in the familiar gradient intercept form, but they're written in, sometimes it's called implicit form, which is different to y equals mx plus c. It's reorganized. Sometimes people will call it the standard form occasionally as well too, but standard form gets used in different ways, so that one can get confusing. But implicit form. So we can see that we have coefficients a1, b1, a2, b2, c1 and c2 there on the other side of the equal signs, and the two variables are x and y. They are also referred to x and y as the two unknowns. There's an example in of three variables in three equations. Okay, so three equations in three unknowns that might be considered. You can see that we've got x, y, and z present in that case there. So systems of linear equations, we study them because they have huge number of applications. Okay, they have applications in pure mathematical sense, but also, as you can see there, things like economics, biology, and physics utilize this mathematics. Looking now at the three cases for two-dimensional or two linear equations in two variables. So basically that's just like what we said here. You can see that we have three different cases that are possible, and in each case we have some examples, comments about the solutions, and geometrical interpretation. So in case one, we've got the example 2x plus y equals 5x minus y equals 4. There's only one solution that's possible. We call that a unique solution. So if you went ahead and used simultaneous equations, either with elimination or substitution, you'd get that solution there, x equals 3, y equals -1. Now the geometrical interpretation of that is two lines there meeting at a point. So we have two straight lines there meeting at one point. Next we have case 2, and case 2 has no solutions, so there are no solutions possible for case 2, and you can see that 2x plus y equals two different things. So even sort of intuitively or logically, you can see there's no solutions, let alone crunching the maths. So we have two distinct parallel lines. So you might be able to see that a bit better if you turned it into the gradient intercept form. So you would have y equals 5 minus 2x, or negative 2x plus 5, versus y equals 7 minus 2x, or negative 2x plus 7. And you can see that they've got the same gradient of -2 in this case, with a different y-intercept, and hence those are distinct parallel lines, and so there's no intersection, so there is no solution in that case there. So that's case number 2. So a unique solution or no solution, or thirdly, we've got a possibility of infinitely many solutions. So we find that the equations, when they're like that, there's a multiple that one of the equations needs to be multiplied by to get exactly the same as the other equation. So you basically have two of the same line, so one right over the top of the other. So that means they're touching at all points, and so there are infinitely many solutions. This is a particular example of the second case here, where we have parallel lines, and we could rearrange it into the gradient intercept form and see that they're lines of the same gradient, but one's been translated vertically compared to the other, or in other words, their intercepts are the only difference. extending this out into the system or the solution of a system of 3 equations in 3 variables, we have different interpretations. When we're talking 3 variables, we're not talking about lines, we're talking about planes. And so we've seen previously in previous videos that ax plus by plus cz equals d is a Cartesian equation to a plane. So you can see that there are 3 equations and 3 unknowns here, and each of them is an example of one of those. So these are 3 planes here. Now the possibilities are listed here. The solution could correspond to the planes meeting at a point, which would be like this one here, and you can see there's a point there that they meet at. The planes could intersect at a line. Common intersection is a line, along a line like that, or a plane, which I haven't shown below, and there may be no solution, which corresponds here as that, for example, we have 3 parallel planes, but also there's where there's no solution to all 3. That's not a common solution there. So these 2 planes do intersect, but the third one doesn't intersect there as well. But we've got these 2 here, these 2 planes intersect there along that line, but this plane here is not involved, and likewise on that. So we're talking about where planes meet, or if there's no solutions, planes not meeting, and this one is called no common solution. So no common solution, or it might be called no common intersection. Of those planes. In fact, you might hear that one a bit more. So no common intersection, and that applies to both of these 2 cases here. Now this, just for completeness of learning, this goes beyond 3, and I've been told that in some examples such as economics, you have many variables. This one here is in general in n-dimensional space, or n unknowns across n equations. Okay, so that's your general case. We'll be limiting ourselves mainly up to 3-dimensional space, or 3 unknowns across 3 equations, but we can go further than that.